software's not perfect. Okay, so just to go over record, I only see Anne, Ryan, and Tori. And here is one more, Chad. Go ahead and grab one of those sheets, Chad. All right, today what we're going to do is go over the level of math that we'll be using throughout the entire year, so not just the first semester. And I have here what we're going to be using in the first weeks. Now, if you want to be precise, these are differential equations. But they're differential equations that are so trivial that we generally just consider them, calculus 1 level. So what these are the definitions of speed or velocity, depending if it's a vector, and acceleration. And so we define the speed as dx dt. Dx dt means, of course, the change in time or in position with respect to time. Now, just a little nomenclature to help tie what we say in general physics class with what we say in this class. In general physics, we will define Vx is equal to, go ahead and grab one of those, is equal to delta x over delta t. That capital Greek delta simply means the change in, or the final minus the initial. So just to make sure I have people correct, you're Hannah, or okay, and you're Jaren, and we still don't have Toussaint or Sally. So this is how they will see it in general physics. That delta means the change. There we go, that's Sally. And when good old Sir Isaac Newton invented calculus, and there is some level of controversy over who invented calculus, was it Leibniz or was it Newton? I firmly believe it was Newton, because Leibniz came to talk to Newton about Newton's new math he'd invented, and then Leibniz published before Newton ever did, because Newton really didn't like to publish. And so that's why there's the controversy. If Newton would have published his calculus when he did it, he would be the one who gets credit. The symbols we use, by the way, are the ones that Leibniz, or however you pronounce his name, the symbols he used. Newton's work was harder to understand and more arcane with the symbols he used. Okay, so when Newton invented calculus, he did so because, school was canceled for the year. We'll talk about this later, because of Black Plague, so he had nothing better to do than physics. And as he was working on physics, came up with his 3 laws of motion, and realized there was no math that allowed him to deal with the continuous changes that his equations were working with. And so he invented a new math, a math he called the math of fluxions, to deal with it. And in its essence, what we're talking about in calculus is talking about minute continuous changes. And so when you use the letter D in calculus, that D means change in, just like this delta means change in. And you might notice that delta, Greek letter, capital D, and D, part of our normal alphabet, a lowercase d, they're the same letter basically, just different language, one's capital, one's lower, because they stand for the same thing. They're both the change in. What is different about these is the D means an infinitesimal change. Whereas the delta, I should have done this in a different color, is a finite change. So you may wonder, what do you mean, oh good sir, by this? And I will tell you. But first I'm changing the color. You can't see what I'm doing right now, correct? Yeah, I guess you can. Well, there, change the color. Infinitesimal means on the order of 1 over infinity. So a dx means you're going from, say, x is equal to 1.000000000 meters to 1 point, all those zeros plus 1 over infinity meters. Right? It's a non-measurably small change. So it's an approximation to continual changing. Whereas when you use delta, it's a finite change. So you might be going from 1.00 meters to 1.01 meters. You know, we can measure that difference. It's measurable. It's finite. So that's the difference in the symbols we use and what they mean. And of course, all the things you've learned in calculus are how we deal with those infinitesimal changes. So I'm going to start with this equation right here and show how we deal with that. Now, first of all, we could have an equation for, and I'm just going to add a new page in here. We could have an equation for position as a function of time. I could have an equation such as x, when I put parentheses t, that means as a function of time, not multiplied by time. It can be confusing, and I'm sure you've all seen that 100 times. Well, more than that. X of t is equal to 35 t squared minus 5t. Let's just say I had that equation. Now, there are units involved. For the purposes of today, I'm not writing the units because we're focusing on the math only. If I want to find the speed as a function of time, that's equal to the derivative of x with respect to time. And so this is a simple polynomial, the simplest kind of derivative other than taking the derivative of a constant. How do you find the derivative of a simple polynomial? Okay, now I'm going to show this very explicitly. And in your homework that you have from today's lecture, this is the only time when I'm going to want you to also show very explicitly how you do it. It's just I want to see that you know how it's done, not that you can find the answer. So, following what Tori said, I bring down the 2, and then I have t raised to the 2 minus 1 because I have to lower that power. And then for the next one, what power do I, or what number do I bring down? The 1. And that's going to be t raised to the 1 minus 1. Of course, t raised to the 0 is just 1. Anything raised to the 0 is 1. So we usually just drop that out, but here you can see explicitly that's why we drop it out, because it's t raised to the 0th power. And so then we just do our math, and Tori had already done the math because, well, you know, many times you'll find a problem that's so simple you can do it in your head and you feel like it's ridiculous to explain it. But the reason that we require the explanations, I went over this with my sophomore in high school son the other day. The reason we require the explanations is so when you get something harder and you can't do it in your head and you can't see exactly how to do it, you have a path, a pattern to follow to get there. So I have 70t minus 5. And so that's how I find the speed at any time given this equation for position. Now the second equation that was on that was the definition of acceleration. Acceleration is the derivative of the speed. My D disappeared. With respect to time. So now that I found the speed, I can take the derivative of the speed and do this. So what's the derivative of 70t?
70.
Minus 0, and I'm not going to write the rest. Right? I brought down my power of 0 from the time that was, I didn't show it because I felt it was stupid to write t to the 0th power, and we know that's 1. But that's where that 0 comes from. And so that's just equal to 70. So this is the very first thing we're going to be doing, except we're going to also want to go the other direction. What if I tell you, and somehow I feel like I'm in some little meme with Samuel L. Jackson when I say that, that I have the acceleration is equal to a constant value of g. And I ask you, instead of going from the position down to the acceleration, I ask you, let's take this acceleration and let us find the position at any time. Then we're going to have to do integrals. And of course, because some people have done this and some haven't, I assume some haven't, it actually should be covered in Calculus 1, but who knows? We start with our A is equal to dV. I used to have a G there, didn't I?
Yeah, it disappeared.
I was like, wow, I was totally prepared. I thought, yeah. Okay, don't disappear on me again. So I have this definition, and this is the condition that I'm running it. In general physics, we will always have this condition of constant acceleration. In this class, we won't. We'll allow there to be, for instance, a jerk. A jerk is the rate at which the acceleration is changing. So if I have this equation and I know my acceleration is a constant, of course I can just put the two together. And this is the equation that I'm going to try to use first. Now I said I want to find position as a function of time. There's no position in this. There's only the speed. But speed relates to position through this equation here. So once I find the speed, I'll go ahead and do it again. I could have written correctly A is equal to d second x dt squared. But we don't have a simple way of doing that calculation. We have to do this in between. So that's why I didn't start with that definition. By the way, here's a shortcut way of writing the second derivative with respect to time. Here's a shortcut way of writing the first derivative with respect to time. When you put a dot over the variable, it means the derivative with respect to time. Now, in your calculus class, you probably learned things like y prime. In physics, if we put the prime, that's going to be a derivative with respect to position. The dot is a derivative with respect to time. The prime is a derivative with respect to position. Right? Most of you saw this, right? Okay. I'm like, really? Maybe calculus teachers have changed the way they do things. So just so you know how to interpret those. Okay, so I'm going to take this. I have my equation, and I need to solve it for v. And as was already said, we're going to have to integrate to get this solved. And the first step is what we call separation of variables. That is, I need to get all of my things that have d's in numerator positions, and all of the variables of one kind on one side, all the variables of the other kind on the other. Separated, so only one type of variable on each side of the equal sign. So to do that, since I need to have, now keep in mind a derivative is technically not a fraction, but we treat it like a fraction. So I just take this and I say, well, if I want to get my d's on opposite sides of the equal sign and in numerator positions, I clearly am going to have to multiply both sides by dt. So I will just multiply both sides by dt. I'll change colors for the multiplication so we can see the... That's multiplied by dt. That's multiplied by dt. Now I can cancel there, and I'm left with dv is equal to g dt. Now this side only depends on speed. This side only depends on time. And so for these two to be equal, I must have some independence, and I can integrate both sides independently and still have an equality. So now I'm going to integrate, and I'll again change signs for the next step. I'll integrate this side from the speed I start with. We use a little 0 to mean the starting, and the speed I end with. And this side I will integrate from the time I started to the time I end. Now, if you read through chapter 1 of the textbook, you'll see that there is a simplification that we assume unless specifically told to do otherwise. And that simplification is to assume that we're going to set our stopwatch so the initial time is 0. That just allows us to put a lot of zeros in and make things simpler. Right? If you're just measuring the time, you're usually free to choose when time 0 is. And so we're going to integrate this side with the limits from time equals 0 to time final. This side from speed at time 0 to speed at our final time. So now we do our integrals. And this is certainly a doable integral for every single one of you. If I integrate it up, I'm going to have on this side v with the limits. On the other side, gt, right? The integral of dv is v. Constants, we don't worry about. The integral of dt is t. Sorry, I'm totally standing in front of you, aren't I?
That's all good.
So now we put in the limits. Now notice I put the limits here explicitly along the way. Once again, for the homework assignment that's due based on today's lecture, I want to see you showing the math like I'm doing here. After that, you can go ahead and do shortcuts, do the things you can do in your head. But this time through, I want to see that you know what's going on, that it's not just kind of guessing or, hey, what is that? 7. Okay. When you put in the limits, you always put in the upper limit first, then the lower limit, and you're subtracting the lower limit. So this is going to be v final minus v initial is equal to g times t final minus 0, or v final. I'm going to rearrange here, and I do assume we can all see this rearrangement. I don't have to put plus v0 on both sides. So there's my equation for the speed, v. You might be wondering why speed is v. And it's because v stands for velocity, which is the vector word for speed. It has speed and direction. And we differentiate velocity versus speed by the arrow over the top. So if I have a v with the arrow over the top, it's velocity. It makes perfect sense. V without the arrow over the top, it's speed. And you have to know it comes from velocity to know why there's a v there. So I have this equation. It's true for any time final. And so we relax it. Relax this to say the speed at any time is equal to the speed you start with plus g multiplied by the time. I took away the final. I just said at any time. So t is that time, and v sub t, or v, parentheses t, is the speed at that time. So now I have an equation for speed as a function of time, and I'm ready to move to the next step. That is v, nice work, is equal to dx dt. Now since I know v is dx dt, I will be able to go through the same type of work to get to the next level. So the first thing I'm going to need to do is replace the v with what I just found. And now I'm going to have to copy this and bring it down to the next page because I ran out of space on that one. And so continuing on, as soon as this page comes up, there's my equation. And now what do I need to do to solve for x? What's the first step I'm going to need to do? Okay, isolate the x from the t, separation of variables. Is that what you're saying, Jerry?
Multiply by dt.
Yep, I do that by multiplying by dt. So I'll take this and multiply both sides by dt. And I have the equation dx is equal to v0 plus gt dt. Left side has only x. The y side has only time as a variable. Now you might say, wait, v was a variable, but that's v sub 0. I was always taught to say v naught. I think it's probably more accurate to say v naught, not for 0. But that's constant. That's the speed you started with. It's not changing. G was a constant, and so time is the only variable there. We're perfect. So now I just integrate up, going from x at time equals 0 to x final. And once again, integrate up from time initial equals 0 to time final. You might ask why I put time final and then have to relax it. It's because it's technically bad math to have the integral dt and then having t as the limit as well. You can't have the limit and the variable of integration the same. That's bad form. And so that's why I have the t final, and then later I change it back to t. Because I don't want to be a bad mathematician, even though I'm a physicist and no one cares. All right, so doing the left side integral, again, I have x, my limits from x0 to x final. The right side integral, what do I have there? What's what?
T limit from 0 from t final to 0.
Okay, I've put brackets with my limits there. And what's inside of the brackets?
Biot-T.
Okay, the first one is going to be Biot-T. What's the second one? Over 2. Now, I did not show this one explicitly. I really should have. When you're doing the integral, you're taking the power that you had, so this was a power of 1. You're raising it, so this is to the power of 1 plus 1. And then you're dividing by that new power, so I'm dividing by that same 1 plus 1. And here, of course, I would have had the 0 plus 1 divided by 0 plus 1. Right? That's where you get those numbers from. After you've learned to do these, you forget those rules and you just put the numbers in. But sometimes it can be important. Okay, so now we put in our limits. Students can make mistakes at this point. Most of what I've done so far, students are pretty up to date on. But putting in limits, I have found that a lot of calculus classes don't emphasize limits very much. You'll learn they exist, but then they just do indefinite integrals, which don't have limits, and you put plus c. In physics, we usually have limits, so instead of putting plus c, we're doing this. So on the left side, of course, x final minus x0. What am I going to have on the right side when I put in my limits? I'm going to rewrite this the way that's easier to read. Yeah, didn't mean to do that. Okay, that's supposed to be an F. I got too close to the edge, and it brings up like the browser and stuff if I get too close. What am I going to have on the right side when I put in those limits?
First one is going to be Biot-T final plus G T final squared over 2 and then minus 0.
Minus again. And what he said is correct. That's minus 0 essentially because each term is 0. You have to put them in to check though. On the homework problem, it's not always going to turn out that way. Even though our lower limit is 0, it's not always going to give you zeros when you put in the lower limits. So you need to go through and make sure. So now, solving this for x final, or relaxing by taking off the f's, x as a function of time is equal to x initial plus v initial t plus 1/2 gt squared. And that is our most important kinematic equation. Like 90% of your kinematic problems are going to be that equation. Now, if you were in the general physics class, I am simply going to give them this equation and say, here is an equation that we can work out. There's a little hand waving, use the definition of average and stuff that you can get there without calculus. But it's, you know, it's kind of a weird derivation, whereas here it's a very straightforward application of calculus. And so that's one of the reasons why I think if you understand calculus, this, you know, the physics 251 helps physics to make more sense, because you can see the reasons why we have these equations instead of that equation kind of just being out of the blue. I kind of have to trust the teacher, right? Trusting the teacher is never the way to learn. The way to learn is to see for yourself how it works. So that is the first equations that we are going to use. And you notice that we had some new things that you probably hadn't learned before, things like separation of variables as an important step along the way, and then integration. All right. Whoops, actually, I need to go back to page 1. You can't go to page 0. It just takes you to a blank page when you go too far. So we have done our work with those equations here. And so I'm just going to move on. Energy and momentum. We'll have energy and momentum considerations later on this semester. And we'll have an equation like this. Work is equal to the integral of force dot dx. Force is going to, of course, be some function of x, we hope. So we can do the integral. But that dot product and the vector signs make it a little more complicated. Dot product means you're multiplying the parallel parts. So down the line, we're going to have to deal with this. How do we do an integral of just the parallel parts? We have the force is minus the gradient of u. U is the potential energy. Gradient. How many people here have ever seen gradient? One. The gradient is a directional derivative. And I know the gradient only in Cartesian coordinates. We also use the gradient in physics a lot in spherical coordinates, but I always have to look it up. So here's what that gradient is in Cartesian coordinates. And I haven't looked yet to see if our textbook uses I hat or x hat for a unit vector. I will use x hat just randomly. And it's usually about this point when people start saying, okay, what's he doing? Did I take the wrong class? I thought this was, just basic calculus that you needed. This isn't really complicated calculus. The most complicated thing is recognizing that that's a z in the final one. I wrote it twice and it still looks clumsy. But we have these d's here. Those are kind of funny looking d's, aren't they? They're kind of a cursive d. Those d's mean a partial derivative. Now, by a show of hands, for how many people does that even make sense to say the word partial derivative? Excellent. That's 3 out of 7. That's almost half. Actually, wow. 8. 7 was the number I thought was in the class. I actually made 8 copies of this, I think, so we're good, but great. So partial derivative, 3/8 of you have heard of partial derivatives. Partial derivatives actually, it seems scary, this new symbol. What does it mean? It means it's easier to take the derivative. A partial derivative means when you take the derivative, if you have more variables than just the one, all the variables that you're not interested in, you treat as a constant. If it's not a partial variable, then you have to worry about, okay, So how does y change with time? How does x change with time? But if it's a partial, if it's x and x is a variable that changes with time, I don't care. I'm only taking derivative with respect to time, and I just say x is constant for my considerations. So the partials are easier derivatives because you get to treat any variable that's not in the denominator here as a constant. So to give you an example, let's suppose that I had u is equal to, let's say what it is approximately on the surface of the Earth, mgy. So if that is my u, and I want to find the force associated with that, I would say, my force vector is equal to minus, and then I have this gradient. So in the x direction, the little x with a hat over it means in the x direction. We divide our directions, three-dimensional space, into x, y, and z, like x, y, z. Each one perpendicular to the others. I guess I better make this z if I'm doing three-dimensional. We usually write as two-dimensional and use y. So minus x hat d dx of mgz minus y hat d dy of mgz minus z hat of d dy mgz. That was a z there, d dz. Now when you look at this, partial derivative with respect to x of mgz, what value is that going to give you?
mgzx.
It gives me a 0 because x is my variable. There's no x here. So everything's a constant. Derivative of constant is 0. What about this one? Derivative with respect to y of mgz. 0 again. Finally, this one, derivative with respect to z of mgz. Mg. So that's the only one that's not 0. So I end up with my force equals minus z hat. The minus z hat tells us it's pointing down. Mg. Now, of course, that's a very simple application of this law, but you can see it works. If you had known that potential energy was mgz, you would see that it worked if you know. So we have this operator with the partial derivatives. I went through that example to illustrate how the partial derivatives work. Power is the rate at which energy changes, dE dt. Well, that's no big deal. Force, this is Newton's second law, and I really should have put net force, is equal to the time derivative of momentum. P is momentum with respect to time. This is actually Newton's second law in its complete form. It's the correct Newton's second law. So when we learn some of the forces, mass times acceleration, that's an approximation for this. It's approximate because mass can change, and if mass changes, some of the forces, mass times acceleration isn't correct. But this equation will always be correct. Then we have calculating the center of mass and the moment of inertia, integrals involving, oh goodness. Somebody asked about second and third derivative, are we doing, or integrals, integrals that are like second or double integrals or third, triple integrals. I don't know why I'm second, third. Double integrals are triple. These here, if I have a two-dimensional space, it's a double integral over area, or a three-dimensional space is a triple integral over volume. Now, as you probably learned in Calculus 1, in most cases that we're going to come up on, you can do this triple integral as a single integral. That is, you can find the area of a shell and then integrate going out on that shell, and it's just a single integral. So when we get to this part, I will talk about using double and triple integrals as well as how to do it as a single integral. But the reason to see these is to see that, yes, there are situations where we'll at least be contemplating the idea of double and triple integrals. Now on to page 2. All right. It seems like a big break between pages, but I'm good with that. Damped harmonic oscillators have this, which is very clearly a differential equation. It's something you're going to see in differential equations if you take it, because it's a very classic differential equation problem. We have a second derivative, a first derivative, no derivative, and then another function of time. I am not going to expect you to solve an equation like that. What I am going to expect you to do is to be able to take x is equal to some function and find its second derivative, find its first derivative, put the function in there, and check to see if it's true. So I'm just going to expect you to check a solution, not to find the solution. This one here, the wave equation, is likewise a second order differential equation, and it has partials in it. It'll be the same thing. I will expect you to be able to check a solution to see if it really is a solution or not, but not to actually find the solutions. Then thermodynamics, we have a new symbol here. See this D with a slash? That's an improper. What does it mean to be improper? Well, when we measure heat and work are the change that occurs in a process. So the heat is how much energy moved from here to here, or the work is how much energy was transferred. They're both transfers of energy. And so when I put this D/Q, I'm actually using what we call the heat. But I'm calling it D heat, hence the improper thing, because it is the change. So when we get there, it's not going to change anything in your math. It's just because Q was already really a D something. And so we have the D/Q to tell us it's improper. We had a little funny thing going on there. And then we have these, the specific heats are derivatives. And once again, if you just ignore that, in fact, most textbooks do ignore that and just put dq dt, then it's nothing new to you. Electromagnetism, that's where the fun starts. That will be second semester when we get to electromagnetism. In general physics, we basically do the same thing as in college physics and general physics first semester. Second semester, there are just things that general physics can't do. Without calculus, you just can't do these things. And so we'll have some more things that we can do second semester because of having calculus. And if you've had differential equations and complex analysis and whatnot, you can really do things with electricity and magnetism. The math there it's not as fun as you would like it to be. So when we get to electromagnetism in the second semester, we're going to have, now this looks familiar, finding the electric field using Coulomb's law. Yeah, just the same as when we found center of mass as far as the way the equations look. But then we have things like this, an integral with a circle. An integral with a circle means it's an integration over a closed whatever it is. So since that's dA, it's going to be an integral over a closed area with no holes in it. We also have integral here that's ds. That's going to be integral of a line that comes back and loops on itself. So that's what the circle means, is that it's over closed space. Things get really fun with the Biot-Savart Law. Biot-Savart Law has an integral with a cross product. It's the most complex of the things we're going to do probably is the Biot-Savart Law. And so those are things to look forward to. Cross product is the perpendicular parts. So you're doing the integral of the perpendicular part of the path to the radius, is what that means. Then we get to quantum physics. In quantum physics, we have things like the time-independent Schrodinger equation. That's this here. That time-independent Schrodinger equation, once again, it's a second-order differential equation. And so we will be checking solutions. We won't be finding the solution. We'll be checking solutions. And that's actually the way we always do it. We know the solution is of this form, and then we find the constants in that form to make the equation correct. We have normalization and orthogonality. That's it. That's our math. Now, I say that's it. That's our math. I say that's it because I finished it, and I got 10 minutes to spare in time. I know for some people, they're going to be like, well, that's not the worst thing in the world. And other people are going to be like, oh, well, I'm going to have some learning to do. I will make sure, as much as I can, to explain the math as we come to it and not just assume, oh, and since you went through this, you know it. Right? Because you probably don't, right? Now, the homework assignment. First of all, you can't see my screen, but I've got things going on that I need to change. You know what? It's probably easier if I just change the computer right now. But no, I can do this. Now that we're back to that, now let's go to this. Go to Moodle. Now, somebody asked about the Moodle page. This is the page to see my son's grades in school. For the Moodle page, it's the same class for, oh, really? There we go. No, it's not Bill. Bill's the old one. Well, crud. There was a link to the new one. It's the same class that we use for general physics. I use the same for both. So, seriously? So, don't worry that it says general physics. I have separate groups, the college physics group and the general physics group. And for instance, this assignment that I am trying to get to, with all the smoothness I can. Okay, this is where there's a flaw. Can't do that. You're going to see all the characters in my password. It's going to be recorded. You can just go on YouTube and watch it over and over. Okay, so I got to change over to this. Maybe I should have just wait. No. Okay, so now that it's hidden, I'm good. All right, thank you for saying that. I don't want to have to change my password. Whoops, didn't want to hit switch user on this either. I'm not going to change over to this until I get my password in. Just so I don't risk doing something really silly. Alrighty, show sesame. All right, so we go to the class here, and we have an assignment that goes with this lecture, and that assignment is grayed out for me because I didn't make myself part of Physics 251 class. You guys should have that show up because you're all assigned to Physics 251. Well, I say you're all. There are, I think, not all of you. I've tried to put everybody in who has an account. Okay, so here is the assignment. So go to the assignment on Moodle, click here, and it brings it up. And it looks disgustingly simple. You know, you only have 2 problems, and each one in 5 pieces. Not nearly as bad as what Rodney Dangerfield had to do in his final exam with 1 question in 26 parts, in case you've ever watched Back to School. Anyway, yeah, and you notice the equations are the same, A, B, C, D, and E. For part 1, you need to show your integral, or excuse me, your derivative. And so you're going to take that and, wow, let me zoom it so you can see it a little better. Over here. Zoom. That'll work. So for the first one, you're doing that derivative, and so you need to show, y equals 5t squared minus 20t plus 17. You can just put y dot if you like. Y dot equals parentheses 2 and parentheses 5t raised to parentheses 2 minus 1 and parentheses minus, parentheses 1, 20t raised to parentheses 1 minus 1 plus parentheses 0. You can stop there. You don't have to put anything after you've got the 0 there. But show it that way. The first one, real simple. What about that second one, though? Y equals 6 over t squared. What do you do when the t is in the denominator instead of the numerator? Easiest thing is to just put it in the numerator. Make it 6t to the minus 2. And then you're going to have, well, bring down minus 2. And then 6t raised to the parentheses minus 2 minus 1. Real simple. The next one, exponentials. How do you take the derivative of an exponential?
Is itself and then times the derivative of that.
It's itself multiplied by the derivative of the exponent. So it's going to be, exponent has derivative of 3. And so it's going to be 3 times 24e to the 3t. Very simple so far. The next one, I have e to the 5t all raised to the 4th power. What would you do there? What's the first step?
Product and chain rule.
Okay, you're going to have to use the product rule, but
Chain rule. So you'll have assuming you already dealt with the 17 in the first thing, then you'd have to bring the 4 down to the outside, so 4 times that, and then you leave the inside alone the first time, and then you multiply that by the derivative of the inside. And then that also has the 5t.
That works. There's another way that simplifies so you don't have to do that. That is, if you simplify the equation first, e to the 5t is, or 5t raised to the 4th power, you just multiply, and so that's the same as e to the 20t. And so it'd be quicker if you put e to the 20t, you don't have to use the second part. Either way works though. So I mean, if you do it that way, that's perfect. But you do have to use the product rule because you have t e to the 20t, or t times e to the 5t all to the 4th power. So you have to use the product rule there. That's why I put it in for the product rule, and to recognize the simplification. And then the last one, natural log. Derivative of natural log gives you 1 over. And you once again have 2 choices. You can either simplify or you can use the chain rule. You can simplify using the rules of logarithms. Natural log of 4t squared is the same as what?
2 times the natural log of 2t.
Okay, that would be 2 times the natural log of 2t. Or you could put natural log of 4 plus 2 times the natural log of t. And that would be the simplest way for doing the derivative, because then you have a constant which you can throw away. There are multiple ways to do it. You need to do the one that works for you. Then we do an integral, and notice these integrals are definite integrals from 0 to t final. All the same equations. The first one should be simple. The second one, if you don't pay attention, you'll get it wrong. It should still be simple. I would say do just like you did before. Make it 6t to the minus 2. Take the integral of 6t to the minus 2. Well, that's going to be 6t to the minus 2 plus 1 divided by minus 2 plus 1, right? Simple enough rule. But then you have to remember putting your limits. And you have to do it right. I'm obviously not telling you everything, but I'm telling you most of what you do. The next one, doing the integral of an exponential. You'll need to figure out how to do that. If Feel free to use integral tables or whatnot to help you remember your math. Number D, that one there, you could use an integral table, or I put it in there before you had to use the product rule. Here you do integration by parts. And my goal is for people to do it by integration by parts. Integration by parts, how many people know integration by parts? Okay, so let me switch over. Kill this. Go back to this. Maybe. Okay, integration by parts. That didn't change it. That will. You have integral of v du That's the basic formalism that we learn for integration by parts. What you do with integration by parts is you find one part that if you take the derivative, it'll become really simple. And you make that the v. And the rest of it becomes the du. So in the equation we had, it was what was it, 7t e to the 20t, I think is what the equation was. And so if this is equal to v du, what part can I take the derivative of and it becomes trivially easy? Which one? The 7t. So I'm going to set v equals 7t. So that means that dv, that's a, in this case my brain was going on to the d before I finished writing the t. So dv will be equal to just 7 dt. And that leaves du is equal to e to the 20t, whoops, dt. So u, to get u, I have to integrate that. You integrate that, you're going to have I think I did that right. And so now I can put those in, and I'm going to have 7t times e to the 20t over 20 for the first part. And then I have to put in my limits going from b to a, or well, a to b, but putting the b limit first and then minus the a. And then for the second one, I'm going to have the integral of e to the 20t over 20 times 7 dt. That's an easy integral. In fact, that's the same integral as we just did right here in our heads, with the exception of having a constant 7. And so then we can do the answer doing integration by parts. Now, are you going to use integration by parts in this class? Maybe, maybe not. It depends on the problems that get assigned. But I just wanted to make sure we had some review on it. Now, the last one that was on that homework sheet, and I can change back to it easily enough now. The last one is going to require you to use L'Hopital's rule. You take the integral of that, you're going to end up with a term that is, in essence, 0 times infinity. Now, L'Hopital's rule is specifically, hey, that doesn't show you the equation. Was it there for a second and it disappeared, or did it never show up? I have it all set right. The next step when that happens is to turn the power off and the switch and turn it back on. It should come up now. So in this case, we're going to have a 0 times infinity. Actually, I think it's 0 times negative infinity. It's t log t is what you're going to have when you put in the limit 0 That's 0 times the natural log of 0, but natural log of 0 is minus infinity. And so what you have to do is rearrange that so that it's in a fraction. And I would rearrange it to natural log of t over t to the minus 1. And then use L'Hopital's rule. Now, I will tell you the outcome. When you apply L'Hopital's rule, you're going to find that 0 natural log of, well, t ln t in the limit as t approaches 0 turns out to be 0. And it will seem like I wasted your time having you use L'Hopital's rule when the answer came out to be 0, which is what you would have guessed if you were naive. But I want to see that people understand that there are situations where you have to apply that. And so I want to see everybody apply L'Hopital's rule for that last one. And if you have to look it up, it's spelled two different ways. L apostrophe hospital or L apostrophe hospital without the S. In both cases, it's pronounced L'Hopital. It's one man. Okay. I'm sorry I went 5 minutes late. I thought I was going to finish early. Let's blame it on technology issues. Any questions for?
Yeah. When's that due then?
When is it due? It's due September 1 after class. Not at class, but at midnight that night, or well, 11:55 that night.
Is that next Tuesday?
Yeah. Next class period, I will have you all demonstrate your solutions.
Fun.
Yeah.
And since it's a PDF, do you want us to
Write it on paper.
rent it out and do it on paper and then scan it?
Yeah, that's my preferred because, I mean, trying to type it in is not fun. I will talk about the scanning in lab today.